Before he joined University of Michigan, he was a postdoc at San Diego National Lab, and he got his PhD degree in MIT and worked with Yusuf on the UQ areas. So he got his bachelor degree from Canada, and so his research interests cover the uncertainty quantifications, optimal design, optimal experiment design under uncertainty. So today he's going to talk about how to use reinforcement learning to help the experiment design. So let's welcome our speaker.
Thank you very much for the introduction, Jianxun. So good afternoon, everyone. Thank you all for being here today. And it is definitely a pleasure for me here to have this opportunity to present some of my work and have a good discussion with everyone. I want to particularly thank Dr. Jianxun Huan for this invitation and Dr. Nicholas Zaboras for coordinating all the seminar series for the center and for making this opportunity possible. Okay, so today I'll be talking about optimal experimental design and the Bayesian design, and I want to focus on some of the latest results that we've been getting for sequential design, leveraging some of the reinforcement learning techniques. Now, before I dive into the sequential design, I do want to present a background, an introduction of what is experimental design and how do we try to tackle such a problem. So let's start with the big picture. Scientific learning, experimental design, or experiments and data are a critical component of scientific learning in general. I particularly like this quote by a famous British statistician, George E.P. Boggs, that said, "Science is a means whereby learning is achieved, not by mere theoretical speculation on the one hand, nor by the undirected accumulation of practical facts on the other, but rather by a motivated iteration between theory and practice. And indeed, with some theoretical understanding, we may produce deductive reasoning to make a prediction of what might happen in the world around us. And we can observe or obtain data from, let's say, experiments to see what actually happens, and compare them and perform an inductive reasoning to go back and update and refine our theoretical understanding." My research area, I focus a lot on uncertainty quantification. So I also want to put those research topics in within this context to see how do they come up in engineering science. Let's take a look at the workflow or some of the components of engineering science research. Often we have theory, and with theory we have models. Could be a computational model, a mathematical model, and models allow us to make predictions. And when we make predictions while taking into account of various sources of uncertainty to that model, that process is often known as uncertainty propagation. And predictions are very useful. We can use them to design good products, make good decisions, good policies. And we might want to do some optimization under uncertainty. Predictions can also be leveraged to design experiments, to get additional data so that we can improve our learning. And these experiments allow us to obtain hopefully useful and informative data, which then we can kind of go back, feed back into the theory and mathematical model part to update our understanding through often known as data analysis, data assimilation, statistical inference, statistical learning. There are various terms that describe that process, but essentially we want to use data to improve our theory and model. So I would say that all of these are some of the critical parts of uncertainty quantification research. And today we're going to look at one particular aspect, which is experimental design. That's situated in this part of this overall flow diagram, and where we're using model to help or to guide designing good experiments so that we can get good data to iteratively improve our model. Okay, when I talk about model, experiments, data, I mean that in a very broad sense. And these experiments could be a laboratory experiment in a very controlled setting. It could be observations in the field. In weather prediction, we might want to release weather balloons to take measurements of the atmosphere. And it could be digital data, virtual data, and the experiment could be the acquisition of data from the usage of certain websites or purchasing data from big companies like Google and Facebook. The experiments could involve human factors. It could be surveys that's presented to different people to get an opinion, perhaps, on some topics. And the experiments can also be adversarial, like in a chess game or a competition, and or perhaps in a military campaign. So the experiment and data is definitely very broad and far-reaching in the context I'm trying to describe them. No matter what these experiments may be, I think we can probably all agree that most of the experiments tend to be very expensive. They can be very time-consuming to perform, very delicate, and in some cases maybe dangerous or risky to the personnel that's involved, or perhaps controversial and have ethical implications. So the research area of experimental design, more specifically statistical experimental design, tries to help us answer some of the questions, such as under what conditions should we perform an experiment? What quantities should we try to measure or try to probe? Where and when should we try to take these measurements? How many experiments do we need? When can we say that we have gathered enough data to answer a particular question? And when do we still need to apply for additional funding to get more experiment and more data in order to answer those questions? So resources are typically limited. So experimental design tries to maximize the bang out of our buck, so to speak. Now, I do want to point out that what I'm going to discuss in this talk are focused on experimental design from a statistical or mathematical point of view. There's definitely a whole different area of domain-specific experimental design. For example, how to set up a particular instrument, how to calibrate them. Maybe you don't want to put these two instruments very close together, that they might interfere. So those domain-specific knowledge about setting up of an experiment are not covered in what I'm trying to discuss today. And I think that overall, if we want to really have a powerful practical data acquisition experiment, we want to combine these statistical points of view along with the expertise of the experimentalist in their particular domains. Okay, so here's the rough outline. I'm going to start with an introduction of Bayesian experimental design. We're going to focus on non-sequential or batch design first. Before then, moving on to sequential design, and in particular, the reinforcement learning techniques that we can really help accelerate our computational process. All right, so just a very broad introduction of the landscape of experimental design literature and also the types of experimental design. Classical statistical design of experiments, or DOE, a lot of these methods are often non-simulation based. You might have heard about space filling designs, factorial designs, Latin hypercube designs. So a lot of these very powerful methods do not require us to have a model. But you might think that if we do have a model that describes our underlying physical process to some extent, it doesn't have to be a perfect model, but it does describe the process to some extent, we can probably also try to leverage that knowledge. And that's what optimal experimental design is trying to accomplish there, that we create some statistical criterion that is based on the model or the simulator that we have, and try to maximize the design, this design criterion based on that knowledge. And in optimal experimental design, when we're performing non-sequential design to begin with, if the model is linear, there's actually been a substantial amount of research, primarily coming from the statistics community. I think it can be traced back starting from almost a century ago. So this is a very established field. And you might have heard about some of these very famous alphabetical design criteria, like A optimal designs, D optimal designs. So they have a very strong foundation. And in fact, much of these criteria have a closed form that allows us to perform efficient design optimization. But if the model is nonlinear, and when I say linear and nonlinear, I'm referring to the model response with respect to the model parameters that we're looking at. If the model is nonlinear, which is often the case when encountering engineering science, the computation of these criteria, they're generally intractable to do. And we have to use some sort of numerical approximation to estimate them. And especially if we want to adopt a decision theoretic framework with an information theoretic criteria, it makes this computation even more challenging. Now, in recent years, there have been a lot of recent numerical advances to try to make this practical and possible to do, especially now we have much stronger computational hardware as well as new algorithms. So in this talk, we're going to focus on try to handle these difficult cases with nonlinear models, expensive models, such as a set of ordinary differential equations or partial differential equations that describe some complex physical process. We're going to look at continuous parameters, design variables, and data variables. And we're going to adopt a Bayesian framework, a Bayesian perspective to quantify the uncertainty and the information that's gained. And we would like to also be able to accommodate in a general non-Gaussian setting as well. Okay, so let's get this started. The first step one here, if we want to design good experiments and the optimal experiment, we need to know what is a good experiment to us. And that very much depends on the goals of the experimentalist or the designer. So for example, if our goal is to learn certain unknown model parameters, then a quantifiable objective, for example, could be that we want to minimize those parameters' uncertainty in some appropriate sense. But if the ultimate goal, what's important is to actually make accurate predictions of those of that model, then perhaps it's better to directly minimize those predictive quantity of interests variance, for instance. We could also be interested in selecting the best model out of a set of candidate models. And in that case, one relevant quantity is this base factor that tells us how good a model is in accordance to some data points that we have. And we can customize this objective function by using a particular loss function that's appropriate to the experimental goals at hand or the mission goals at hand here. And I think this is an interesting area because I feel that often we probably don't know exactly what we want to do from an experiment, or at least it's not immediately obvious how to translate that into a mathematical quantity. And there's a lot of interesting science behind how to, in a sense, map what we want from our head into a formula or equation in the statistical sciences study there. Okay, so for this presentation, let's assume we're interested in the first goal here. We want to learn some model parameter, and we're going to minimize the parameter uncertainty for illustration. Okay, all right, so step two. Let's have a mathematical framework to quantify the uncertainty here. And the framework we're using is probability theory, and in particular, Bayes' theorem for updating the uncertainty. So here, theta denotes the unknown parameters that we're trying to learn, and y denotes the noisy data, the experimental data that we measure. Before we do any experiments, before we have any data, we have what's known as a prior probability distribution. For instance, here's a cartoon of what it might look like. So this describes our state of uncertainty about the unknown theta values before we have any data, hence the name prior. And we can multiply this prior by a likelihood function, so which is the probability density of observing the data y if the theta values were actually those values. So it's how likely is it for us to have observed those data measurements. And the likelihood function is the key mechanism that allows us to perform the statistical inference or the data assimilation. When multiplying these two quantities together and normalize it with what's known as the evidence term, such that it stays a proper probability density function, we obtain the posterior distribution on the left-hand side here. And pictorially, maybe it looks something like that. And the posterior is a reflection of our state of uncertainty about theta, conditioned on having obtained or observed this data point from the experiment. So we have some new information now, and hopefully the posterior, roughly speaking, it will shrink a little bit. So the uncertainty is reduced from that extra data point. So loosely speaking, the shape of the posterior and the narrowness or the wideness of the distribution is a reflection of how much uncertainty we have reduced or how much information we have gained. But the extent of this uncertainty reduction is dependent on which experiment we do, which comes back to the experimental design problem. And therefore, all of these terms that I have displayed here are all conditioned on the design variable D. So that's where we're going to do our optimization. Now we can be more precise about quantifying this extent of uncertainty reduction or information gain. And that leads to the next slide here, the formulation of the objective function. And here, we're going to use this quantity called the Kovac-Leibler divergence between the posterior distribution to the prior distribution. So this Kovac-Leibler or KL divergence, in a sense, is a reflection of how different two probability distributions are. And the idea, the intuition here is that if the posterior, which is the after, prior is the before, so posterior is the after uncertainty distribution, if it's very different from the prior, that means the data we have obtained from the experiment is very informative to update our belief or change our mind because we have a stronger evidence. So generally speaking, we want to kind of maximize this difference between the posterior to prior. In fact, it is also equal to this mutual information between the data and the parameters that we have gained, this information we had gained from performing that particular experiment. So here, this blue quantity is the Kovac-Leibler divergence. Now, of course, when we're designing this experiment, we haven't done it yet. So we don't know what this measurement would be. And the Bayesian thing to do, so to speak, is to take the expectation of all possible data realizations conditioned on performing that experiment. So we get this average or expected information gain or expected utility. Now this quantity here overall, which if we write it out in terms of integrals, it is like that. It's intractable to compute. There's no closed form unless our model is linear. It has to be approximated numerically. So you can imagine that this might be a very expensive thing to do. So I'm going to propose one possible way to estimate this quantity. Since we have integrals here, and after some algebra, we can establish a Monte Carlo estimator to this expected utility quantity that's shown here. And Monte Carlo just means sampling. We're going to generate samples of the parameter from the prior, so we know how to do that. And we're going to generate the samples of the data from the likelihood function, and we know how to do that. So it seems like this is a promising approach there. But in this Monte Carlo estimator, there's this red term here, and that's a very pesky, nasty term. That's the normalization constant in Bayes theorem. And that generally is very difficult to estimate and has no closed form. So in this case, we elect to use another Monte Carlo estimator just to estimate this red term here. So overall, we have a Monte Carlo estimator inside a Monte Carlo estimator and a so-called double-nested Monte Carlo estimator. And each of the samples in the Monte Carlo requires a model simulation. So if we have m samples and n samples, then in total we need m times n model evaluations just to estimate this quantity at this design. And overall, we still need to optimize this quantity in the design space. So this can quickly become very expensive to do. Nonetheless, we have a way to estimate this objective function. So we can go back and make our problem statement. The optimal experimental design problem is to find the best D or D star that maximizes our expected utility function U. If we use the Monte Carlo estimator from the previous page, then our estimate or evaluation of this U is noisy, because Monte Carlo is based on sampling. Sampling has noise. And we need to then perform an optimization that can accommodate noisy estimates of the objective function. And there are particular types of optimization routines or algorithms that are more suitable to do that. For instance, one that we looked at is this Robinson-Monroe stochastic approximation. And if you're familiar with this, this is also the basis of stochastic gradient descent. And the idea is that essentially we're doing steepest descent, and we can do that even if we, or we can do that if we have access to an unbiased estimator of the gradient. So it's still some sort of gradient-based optimization algorithm. And here, for instance, I plotted out for one scenario the actual objective surface. You can see that even with a reasonable sample size, it's still quite noisy. And I also want to note that we are maximizing here. We're not minimizing. So the optimal points are at the corners, not this point in the center. So it can be a challenging problem. It's definitely non-convex, so to speak. But this optimizer seems like it does reasonably well. Starting here, it walks around towards a corner here. But if we want to use this optimization algorithm, we need some gradient or derivative information, which in general, especially for black box type of models for complex physical processes, we may not have access to them. So one approach or strategy we take is that let's build some surrogate models where they have some friendly or nice forms so that we can take derivatives very easily. And also building a surrogate model can really help accelerate the computational process to alleviate the need of m times n model evaluations that we need from the Monte Carlo estimator. So the choice of surrogate models is quite open. There are many different possible choices that one may use. I'm going to briefly present one option that we looked at in one of our past studies, but it's definitely not tied to choosing this to choose this surrogate model. So we have looked at a polynomial case surrogate model, which is essentially a, let's say, polynomial basis expansion of a random variable. And here the basis functions are orthogonal polynomials, and constructing the surrogate involves computing the expansion coefficients. There are different ways to estimate these expansion coefficients. If the dimension of this problem is not too high, we can perform a projection and use for example, a quadrature calculation of this integral, especially if we expect smooth responses. And quadrature, not necessarily using the tensor product quadrature, but we can also use sparse quadrature, and sparse quadrature that's adaptive in different dimensions as it detects the nonlinearity. If it's more nonlinear in this dimension, it can add more quadrature points there. So that can help us to handle higher dimensions. And you can see that if we have access to the surrogate model, then we can get the derivative information very easily because we're dealing with polynomials in this case. Like I said, this is not the only choice. We can definitely use other surrogate models like Gaussian processes, deep neural networks, random forests. But I think whatever we choose, hopefully it has a nice form that at least we can evaluate very quickly, get good accuracy, and in this case, get the derivative information very fast. Okay, so let's take a look at some quick results. So here, I'm looking at the design of a combustion experiment. And here we have a shock tube experiment. So in the laboratory, in order to test the property of new fuels, so fuels for, let's say, automotives or airplanes, and to learn them, one experiment is the shock experiments where you fill a shock tube with a mixture of the fuel and oxidizer. And then you have a diaphragm with a high pressure gas in one region, and you kind of puncture the diaphragm, and then you have a shock propagating through the tube. And where the shock passes through, the temperature and pressure is raised almost instantaneously. So shock is kind of this continuous phenomenon. And the measurement in those experiments often is we can measure this ignition delay time. So how fast or how slow did the ignition occur once the temperature is raised down. And that measurement of the ignition delay can tell us a lot about these kinetic properties or kinetic parameters in the mechanism that describes that particular fuel. So it's a very useful experiment there. And here, we're assuming that we're interested in learning two particular kinetic parameters in a much bigger, detailed chemical mechanism. In particular, there are the pre-exponential factor of this elementary reaction and the activation energy of this particular elementary reaction. The design variables, so these are the knobs that we have control over for performing this experiment, are the initial temperature and the equivalence ratio, so how much fuel that we put in the system. And on the bottom left, I am plotting the objective function. I kind of brute forced it in this case. So the higher objective values, so the red regions, are informative experiments. And we're comparing, let's say hypothetically, we did an experiment under this condition, A, versus this condition, B, versus this condition, C. Let's see how the posterior, the residual uncertainty, looks like. That's what I'm plotting on the bottom right here, A, B, and C. And the posteriors, the probability distributions, are two-dimensional, because we have two unknown parameters. And we can see that indeed this high objective design condition A gives us a posterior that's much more narrower. So we have a more confident estimate of these parameters. Whereas B and C, they're not as informative. The posteriors are relatively speaking wider. So there's more residual uncertainty there. Okay. So that's a nice kind of validation that our framework is indeed working. Here I'm showing another example. We're looking at a diffusion phenomena, partial differential equation in a square domain. And here we have a source that's a chemical that's diffusing out over time. And what our goal is to infer the uncertain source location. So we don't know where that source is. We want to take measurements so that we can infer or estimate where that leak of contaminant is. The measurements are the concentration of this contaminant at 5 equally spaced times. So we're not going to optimize of when to measure. We're going to assume that's fixed. But we're going to optimize where to measure. So we can put a sensor location in this domain here. So the objective looks like this, and that's what I have illustrated earlier, where the best locations are at the corners. So when I look at this problem at first, if somebody asked me, I have a square domain in a diffusion field, you have one sensor to place, what's the best place to put it? My initial reaction is I will put it in the middle, because in some sense that has the best average coverage of this square domain. But according to this expected utility, this objective function, that's precisely the worst place to put it. We're maximizing, right? On the right here is the numerical results. When we do this optimization many, many times, we see the numerical optimizer do converge mostly to the four corners. And that phenomenon is very counterintuitive to me, and I wanted to understand why it's best to put at the corners. And we can see that by looking at some posterior distributions. So here, I'm plotting the two-dimensional posterior distribution, which is like where the source location is in the square domain. And here, the sensor on this plot, on the left plot, the sensor is at the bottom left, and the true source location is at the blue circle here. And in this middle plot, the sensor is placed at the top left. And on the right here, the sensor is placed at the middle. And we can see the posterior in each of these three candidate designs. A couple observations. One is that we see, in almost all cases, we have kind of arc of a circle or semicircular type of shape to this posterior. And that can be understood from a physics point of view. In a diffusion field, diffusion is isotropic. If you take one measurement, you can learn something about how far the source is from you. But it doesn't tell you about direction, because diffusion is isotropic. That's why we have all these kind of almost semicircular or circular shapes. Near the boundary here, that's because of the boundary constraints that we're applying. The other observation is that, roughly speaking, this coverage of these of the area is some sense how much residual uncertainty that we have. So we want this posterior to be narrow or to be small. So in this particular case, we see that maybe one can argue all three designs are fairly equal area coverage. Maybe even this one is better on the right. But this is under one case where the true source location is at the blue point. But we don't know that ahead of time when we're designing the experiment. It could be, in fact, could be over here, could be over here, could be over here, could be anywhere in this domain in accordance to our prior understanding of these source parameters. So for instance, under another scenario where the source is actually close to the bottom left here, we see that out of these three designs, the bottom left sensor is the best out of the three because it has the narrowest uncertainty distribution. So what the point I'm trying to make is that this experimental design procedure looks for the best location to place the sensor on average over all possible scenarios where the source might be. And it turns out that due to the specific square geometry and the diffusion process that we have here, the best cases are actually at the corners rather than at the center there. One natural question you might ask is, what if we have two measurements or two sensors to place? That would be an excellent question. So let's take a look. On the next slide, I'm going to show the posteriors with two measurements. For the left column, I'm just going to double up the sensor at bottom left. So I'm going to put the two sensors at the same location here. In the middle, we already have a sensor at the top left. I'm going to put another one on the bottom left. And on the right, we have a sensor in the middle. I'm going to double up in the middle. So let's focus on the left column here. So this is with one sensor. This is with two sensors. So 1, 2. So we see that the posterior shapes are roughly the same, and they have shrunk a little bit because we did get extra data point, but not too much change. And let's focus on the right column. This is with one sensor, 2, 1, 2. So again, it's similar shape, but it shrunk a little bit, but not too much of a change. And if we go back to the center column here, this is 1, only just top left. And this is 2 with another one on the bottom left. 1 and 2. We see a drastic shrinking of this posterior uncertainty. And in this case, that we can, again, make a physics-based interpretation is that we actually have two different locations. So in a sense, we're triangulating, so to speak, that we can really get a good estimate also of the direction of the source, and rather than just the distance, because we have two different angles to sense this source, to sense this concentration. The main message what I'm trying to get across is that if we can do multiple experiments, it's not always the best to repeat the single best experiment multiple times, but there is value in co-designing them simultaneously because there could be nice interactions and coordination among the different experiments. All right, let's go to sequential design. So sequential design, the scenario is that we can now perform multiple experiments and potentially one after the other in sequence. And now you can think there are potential additional advantages we can obtain. Before I forget, I do want to mention that the reinforcement learning sequential design I'm going to present in the next few slides are conducted jointly with my student Huan, so he did all the hard work there. Okay, so in the sequential design, if we can do multiple experiments and we do a batch or non-sequential design, you can now see that perhaps we're missing out on something, because if we design them simultaneously, we're not leaving room to update or to adapt between the experiments when new observations are being made. So we don't have that opportunity. So there's no feedback for non-adaptive, and overall it's not optimal. Another possible design approach where we do allow update in between experiments is a greedy design or a myopic design. And the idea is that we can design for the next upcoming experiment optimally, okay? And then we do it, and then we use the new data to update our understanding, update our posterior distribution, and based on the new updated scenario, we plan for the next upcoming experiment optimally and do it. So greedily do the next optimal step one at a time. So this allows adaptation, but it does not have look ahead or no coordination among the different experiments. If we know that in total we can do 3 experiments, for example, that's some useful information there. It can help our planning, and especially if we have a model that is predictive, that we can get some sense of what the consequences are in the future based on our action right now, it can help us make a better decision today. Okay, so a fully optimal sequential design process for a finite number of experiments, we want both the properties of feedback and look ahead. And we can formulate that, but solving that problem is extremely challenging. So you can imagine if we want to simulate all different possibilities into the future, that's a lot of simulation, a lot of computation. So it's very expensive to do. And in the experimental design research, the works that do take this fully optimal design framework are often limited to discrete variables or leverage special problem property or solution structures. We also have taken a look at a procedure using approximate dynamic programming to try to tackle this. We've got some fruitful results, but definitely one conclusion is that it's very expensive. So we want to try to make this optimal formulation practical. Okay, so just to give you some more intuition about this concept of feedback and look ahead. So here, if we do a non-sequential design, here where we have this contaminant that's dispersing out and there's wind pushing it around, we have a prior distribution of where we think this leak of contaminant is. We're flying a UAV around to take measurements in sequence. What would our design look like? It might look like something like this, where we fly to the best location to take a measurement a priori, and then kind of just follow it as this entire plume is pushed around by the wind. So there is no feedback or adaptation there. Sequential design allows feedback. So we can fly to an initial location, take a measurement, and use that information to update. So you see that the posterior has shrunk a little bit. And based on this new setting, we can plan better for the next step to go. And here, we can then go to the next one and next one. So overall process, hopefully, is more efficient to achieve our experimental goals. The aspect to look at is maybe in this case, the wind is pushing this plume towards our home base, let's say, then our first experiment, maybe we don't need to spend a lot of fuel to fly way out there to take a good measurement. If we know that we're going to do 3 measurements, and rather wait for this wind to carry it over, and we can take a smaller step to set us up better for a good measurement in experiment 2 and 3 at a slight sacrifice in experiment 1. So that's the benefit of looking ahead into the future. Okay, so the scope of our work is very similar to before. We're going to look at finite number of experiments. We're going to look at nonlinear, potentially expensive models, continuous spaces, Bayesian framework, non-Gaussian distributions, and information design objective. And this is where the reinforcement learning really can help us here. So we want to enable fast, optimal design of sequential experiments. And we're going to show that some results using reinforcement learning. What is reinforcement learning? Let's briefly describe that. In reinforcement learning, often we have an agent, and I'm presenting that as a brain, the picture of a brain here. And the agent has some understanding of the state, and the state could be about the agent itself, the system. It could be about the environment, how the world works, the rules of reality, so to speak. And the agent can take actions, so this action here, to interact with the environment. And when an action is taken or an interaction is performed, observations can be made from what happened. And also there could be a reward that tells the agent whatever you did, was it a good thing or a bad thing, based on some measure of utility there. So the idea then is how do we, by performing actions, how do we reinforce our learning of the rule of the world so that we can maximize the reward to this agent? How does this relate to sequential experimental design? Well, the action is designing and conducting an experiment. So we're choosing which experiment to do and do it. And the reward is our utility function. So essentially, for example, how much information we have gained from performing that experiment, and also how much cost do we have to dish out to do that experiment. So to solve this problem, we need a couple items here. The first is a policy, also known as an actor. So this is the rule that we want to follow to perform our actions, or in this case, to conduct our experiments. And this rule is depends on what our current state is, because depending on the situation, we probably want to take a different action there. And this is what is a good rule, a good policy is initially unknown. So we want to learn what is a good policy here. The other unknown entity is this reward, which is also known as a value function or critic. So this is the function that tells us, based on an action we take, and how good is that action, because every action has a consequence associated with it. And in solving a reinforcement learning problem, it often comes down to finding a good policy or finding the value function that governs how the world works. And broadly speaking, there are two, or maybe let's say 3 strategies of reinforcement learning algorithms. One is we can target to construct or learn these value functions, and they're value-based reinforcement learning. Another one is instead, let's try to learn the policy, and those are policy-based. And then there are also these hybrids that learns both value functions and policy, and they're often known as actor-critic. So actor is the policy, and critic is the value function. And in a lot of the literature, the work, it seems that actor-critic-based algorithms have really good performance. And we're going to use one of these actor-critic strategies in the sequential design problem. All right, so some mathematical components that we need to set up the problem. First is the experiment index. Index is k, going from 0 to n minus 1, so a finite number of experiments. And we assume we know how many experiments that we're going to do precisely. Then we have a state variable, xk. So this is the state after we have done k experiments. So the state variable should be very comprehensive. It should include all the necessary information for us to make all subsequent decisions in an optimal manner. So it's a very kind of perfect thing, has all the information we need. It's often broken down into two main components. The belief state, which describes our state of uncertainty. For example, that could be our posterior distribution. And the physical state that describes the physical process, like the GPS coordinates of our UAV right now. And K here is just which experiment we're at. We can also group that into the state variable itself. The policy, often denoted by pi, involves a function, which I call it the policy function u pi, where now what experimental design we want to do is the output of evaluating this policy function at the given current state. So we want to know that what's the best thing to do depending on our current situation. So we're no longer finding optimal designs per se, but we're finding the best policy or best strategies in selecting our design adaptively based on our current situation. So that's what this policy function means. Observation, still the same notation y. We also need some reward functions or negative cost functions. Stage reward are the rewards associated with performing each individual experiment, so the kth experiment. And for instance, it could be the negative cost of performing that experiment or that action. Then we can also have a terminal reward that assesses how well we have done our job after all the experiments are done. And in this case, if we care about learning model parameters, it could again be the information gain after the final posterior compared to the initial prior. So how much information we gain there. We also need a system dynamics, which describes the evolution from one stage to the next. So for the belief state, the posterior, that can be the base theorem. That would be the natural choice there. For the physical state, it could be whatever the physical process that governs that state. For example, if it's the position of our aircraft, then the position at the next experiment is the previous position plus the displacement as a result of performing the previous experiment there. So it could be something as simple as that. All right, so let's state the problem. Here we have the expected utility for sequential experimental design. So U now is a function of, or functional of our policy pi. And it's, writing it out, it's simply the sum of all stage rewards plus the terminal reward. So it's the sum of all rewards. But we need to take the expectation because we don't know what measurements we're going to get when we're designing these experiments. So we take the expectation again. So the sequential optimal experimental design problem is to find the policy, the optimal policy pi star that maximizes the U of pi, subject to any of the system dynamics, how the system evolves, or any design constraints that we may have. How do we solve this? One possible way is to recast this problem as a dynamic program, leveraging Bellman's principle of optimality. So transforming the same problem into these equations. So here what we have, these V functions are value functions, which represents the best achievable value from the remaining experiment. So if we're at the experiment K, so all the remaining experiment, what's the best achievable value or achievable reward? And it's the maximum of the expected reward from doing this upcoming experiment plus the best achievable reward from the next experiment onwards. So it's a recursive definition, which means it's hard to solve. There are many different algorithms, strategies being developed in various fields related to this, like in optimal control, stochastic control, in operations research, and largely speaking, there's a wide body of research under approximate dynamic programming that allows us to try to find a solution numerically and approximately. So we took a look at this before, and it can become quite expensive. So we're going to take a different perspective here this time. And we're going to use this actor-critic type of approach. So actor-critic, we're going to approximate or construct a good policy and value function concurrently. So to explicitly approximate that, let's parameterize our policy. So instead of pi, everywhere we had pi before, assume we have parameterized it. We use a function approximation, parameterize it, and W is the parameters of that policy function. For example, if we use a deep neural network, W represents all the weights and bias parameters of that deep neural network. We are then searching in the parameter space to maximize U. Okay, good. But that's half the story here. We have parameterized the policy. We also need to estimate the value function. And we don't know the optimal value function ahead of time. That's the problem we're trying to solve. But for a given policy, mu W, we can estimate the corresponding value function corresponding to that policy that's given to us. And we can estimate that numerically. So here, this Q function is the action value function, because this is a value function that depends on not just the state, but also the action or the design itself. So this is saying what is the best achievable value for all remaining experiments if we're currently at this state, and if we take this next action or perform the next experiment as this. And we can simulate this, the trajectory that follows by using Monte Carlo, and estimate the rewards that we obtain by performing these, by taking this particular action there. And once we have these estimates, again, we can perform a function approximation of these action value functions. For instance, use another deep neural network or your favorite function approximator. For instance, we can also do that using a regression. Okay? Then we need to estimate the policy gradient if we want to optimize this policy using a gradient-based optimization algorithm. So the gradient is, what we want to get is the gradient of the objective function U, or the expected utility U, with respect to the policy parameters W. So we want to find good policy, right? So we want the gradient with respect to policy. This will involve some math, which I'm skipping on the math, but after some derivation, we can again construct a Monte Carlo-based estimator to approximate this gradient, which then requires us to have the gradient of this policy function with respect to W, as well as the gradient of the action value function with respect to the action that we're taking. So in a sense, this gives you some notion of chain rule that's been embedded in there. And if we choose good functional approximations or representations of the policy and the value function, we can compute these. And therefore, we can estimate this. And once we have the gradient with respect to the policy parameters, we can throw a gradient-based optimization algorithm to try to find a good policy. And that's what we're going to do here. So this pseudocode is known as a deterministic policy gradient, or DPG. And roughly speaking, we're going to initialize the policy and value function approximations. And then we're going to simulate designs and data that follows the current policy estimate, that Monte Carlo simulation into the future. And using that, we can update or construct our value function through, let's say, regression. And that once we have both of those, we can then calculate the gradient of the objective function with respect to the policy parameters, and then perform a steepest descent type of update in finding a better policy. And we can iterate by going back to step 2. So simulate samples. From the samples, we update the value function. With the value function, we can compute the gradient and perform the policy improvement, and we can iterate this process here. There is also a recent work known as deep deterministic policy gradient, which essentially is to use deep neural networks as the functional approximators, and it has shown some pretty good success. All right, quickly some results. Time's flying by. So first, we're doing a benchmark problem where we're looking at a linear model with Gaussian priors. So we have a conjugate system where posteriors are analytically Gaussian, and we have closed form formulas for it, which means that in the sequential design problem, we have the exact solution. We can get the exact solution, so we can benchmark it. And here I'm plotting the true objective function and the true policy front. So anywhere, if our policy stays on this front, we're optimal. And here we solved it numerically using dynamic programming, using policy gradient. They both stay within this front, and we can perform many, many simulations to see what is the expected reward. And we see that the expected reward are very close to the analytical exact solution. So that's good. We have a sanity check there. And what I want to point out is the computational efficiency. So here I'm showing the convergence of the reward from performing the policy gradient as a function of iteration. And the red line is the true value. And we can see even after maybe 10 iterations, we're pretty much there. But we purposely overkilled it by running into 100 iterations. And the training time, 421 seconds, involve only 90 million model evaluations, which is substantially lower than when we needed to use dynamic programming, which required almost an order of magnitude higher in terms of time. And the testing time, so to use that policy that we have constructed, is also very fast. 42 seconds for policy gradients, and for dynamic programming, it's I think that's probably 5 hours, so much, much longer. Policy gradient is definitely giving us very promising results in terms of performance. How does this benefit us in the sequential design context? So we're going to go back to the two-dimensional diffusion problem. I'm going to skip all the details here, but what I want to point out is that to highlight the benefit, we're purposefully designing the problem such the source is off initially until 0.16 seconds, and then it turns on. So there's a switch. It's off and then comes on. And the diffusion field might be like this: 0 seconds, nothing is here. 0.16 seconds, nothing is on yet. And then the next after that, 0.24, the source has been switched on, and we have diffusion. Okay, we're going to look at the design 2 experiments. The first experiment is before the source is switched on, and the second experiment is after. And we specifically designed it to showcase the value of looking ahead. We're trying to infer the source location, and the sensor starting location is in the middle. So imagine we have a truck we can drive around to take measurements. We can't just go anywhere. There's a range constraint on how far the truck can drive to. And there's also a cost associated with driving long distance. Okay, I'm going to skip this part. Okay, so keep the intuition in mind from the earlier discussions that the good locations to take measurements are at the corners, not at the center. It's the same problem that we're looking at here. Now let's compare. Here we have greedy design strategy on the right. We have sequential optimal experimental design, the optimal formulation on the left. And I'm displaying time and also the accumulated reward as we do multiple experiments. On the left plot, I have the actual diffusion field, and on the right, we have the belief state, which is the prior posterior update. Okay, so for the first experiment, greedy design, we don't move. This is our truck. Because it knows that the first experiment is before the switch is on, so it's smart. It doesn't move because we don't measure anything. And if we move, then we're wasting energy because there's a penalty on movement. Now SOED, it does move. It moves a little bit towards one of the corners. Because the reason is because it has this look ahead. It knows that the source is going to be switched on later in the second experiment. And we know that corners are good, so it's already getting a head start to move towards that direction at an initial sacrifice. So by making that movement, it accumulates a negative reward or a cost in the first experiment. But then in the second experiment, where now the source is on, Greedy now realizes, oh, let's start get going. But it can't go all the way up to the corner, so it can only make a certain distance towards the corner, so in this case here. Whereas in the second experiment, the optimal design strategy, it's already made a head start, so it can make another step that is not much closer to what we know is a very informative sensing location. And indeed, after 2 experiments, the accumulated reward for the optimal design strategy is higher than the greedy strategy. But of course, this is one possible scenario where the true location is here, but the true location could be here, could be here, could be anywhere in this domain. So we want to simulate this many, many times to find the expected reward. And we do that. And we see that the average expected reward for the optimal formulation, 0.614, is indeed higher than the greedy 0.558 here. So that is also a nice confirmation. There is value in this case of looking ahead. Okay, I am quite over time, so I'm going to stop here and leave the summary here. Or before that, I do want to acknowledge and thank again Jian Xun and Dr. Zavaras for this opportunity, and the collaborators, especially Wang Gangshen, for a lot of the hard work. Great, thank you.
Thank you. So we're a little bit over the time, so let's just 1 or 2 short questions.
I have a quick question.
Sure.
So in your learning process, you said you have 2 types of rewards, terminal reward and state reward.
Yes.
It seems that state reward would be sufficient. Why do you also need terminal reward?
Right, so terminal reward is, in a sense, a catch-all. Essentially, like if we have some measure of goodness on how we perform that's not specifically tied to an experiment, we can just group it to the terminal reward. So in this case, I'm putting all the information gain into the terminal reward, and I'm letting the stage reward just be the individual cost of performing the experiment. But that's not always the only option. I can also divide out the information gain into incremental information gain between experiments and look at the summation overall. That's definitely another possible strategy. But yeah, it's just another way to inject additional criteria if you have it at the end there. Thank you.
Source inversion what are the assumptions and also have you considered multiple sources? Does it generalize to one source of
Good question. So there definitely are many assumptions involved in each of these examples I have shown. So definitely in the source inversion problem, the governing equation, I'm assuming it's governed by a scalar diffusion process. I'm assuming there's no convection. I'm assuming the diffusivity is homogeneous and isotropic. So everything that comes into it, the boundary conditions, also all of those are assumptions. What was the other question? Oh, multiple sources. Yes. So I have not particularly looked at the performance or design of learning multiple sources, but the framework can definitely be used under that scenario. In that case, if we have, let's say, 2 point source or centers of 2 point centers, or not centers anymore, but let's say 2 locations of the source field that we want to infer. Let's say it has 2 bumps, then we can put that together. We can have an overall 4-dimensional parameter vector, and we can try to learn that simultaneously. So the dimension will be higher, but the framework can be exercised as presented there.
So do you think the framework is also generalizable to the situation where you have multiple, say, people taking measurements and maybe having like a partial knowledge of what the other people do?
I think that's super interesting. I do not think we can directly use what I presented in that case because I think it's a lot more complicated. I think what you're describing, I thought briefly about this. We have imperfect information about what other people, so it's not a hive mind or mastermind that knows everything that's being done. There could be asynchronous introduction of information. Maybe the first person finishes first and the second person finishes a little bit later. So how do you synchronize it? Yeah, I think that requires some additional algorithm development. I think it's super interesting, and what we have here, not quite ready for that. Okay. But yeah, maybe we should talk to do that. Yeah.
Thanks.
Okay, so let's thank our speaker again.
Great. Thank you.